Good afternoon. Now, this is lecture number 38, and already we have started discussion about volume of fluid method. So, we will try to see today in volume of fluid about the different reconstruction methods. Okay, so in volume of fluid, as I have specified you earlier, that there are two types of approaches. One is interface reconstruction method, and second is interface advection step. Okay, so right now in the yesterday's class, what I have done, actually I have mainly explained you about the interface evolution in one dimensional system, and then we have initially started the discussion on two dimensional systems, and particularly for two dimensional systems, how volume of fluid ensures the conservation of mass. That is something which I have discussed. Okay, now I will discuss about the 3-4 methods which can be employed for reconstruction of the interface. So what are the issues with these methods, and what are the say advantages of one over the other, that I will take up in this. And after that, though earlier I told that I will discuss about the advection schemes for 2D as well, but that part I will not discuss. In last lecture I will present the volume of fluid as a whole. So starting from the governing equations, then averaging of the properties, then discretization of these governing equations, and how finally whenever we say uses some software using the volume of fluid method, then what type of outputs actually we get. Okay, so that is something which we will discuss in the last class. So as a whole, how volume of fluid method is working in practical scenarios, only that aspect we will discuss. Okay. So, interface reconstruction is our present topic. So, in terms of interface reconstruction, we know that when we are working in the two-dimensional system, okay, so typically we have come to know that PLIC and Hart and Nicholas VOF are having some challenges which leads to unphysical pinch off, like unphysical breakup and coalescence of the interfaces. Okay, so to avoid that, yesterday we have seen that there is this concept of piecewise linear interface calculation, where rather than specifying a horizontal or vertical line, what we do in case of the earlier two techniques, here we present a line segment at certain inclination. Okay, and that inclination is nothing but decided by the direction of the normal vector. Okay, so direction of normal vector, we have calculated m as nothing but gradient of color function. Okay, so gradient of color function will be giving me the direction which is normal. Now, if you have to find out the unit normal vector, then unit normal vector will be nothing but m vector divided by magnitude of the m vector. Okay, if m I consider as gradient of c. Now, once I know the c, once I know this m, then I can do m dot into x equal to alpha, where m dot into x is nothing but the equation of line, and alpha is the intercept, that at what location I need to specify the line. Okay, for example, if you have a cell, in this particular cell you can place, say you know the slope of the line m, then you can place this line at this place, you can place this line at this place, you can place this line at this place. So for all these different set of lines, your value of slope is equal to m only. Okay, but the exact intercept where you will be placing the line, that is something which we call as alpha. And to determine alpha, what we can do, the cell in which we are reconstructing the profile of the interface, we know the value of color function for this cell, and I know the volume of this cell. So if this is a two-dimensional cell, then volume of the cell will be x square, and x square when multiplied with Cj, that will give me the, or in a two-dimensional system I must write it as Cij. Okay, so when x square is multiplied with Cij, fraction of the reference phase, then it will give me nothing but the volume or equivalent area which is occupied by this particular which is occupied by reference phase in this particular cell. Okay, so whenever you will be placing this line, you have to select the location of the line in such a way so that the area covered by this line, okay, the area covered by this line is nothing but identical to h square into Cij. Is this point clear? All are clear with this point? So whatever the area this line will be enclosing, that has to be equal to h square into Cij, then only we will be able to represent properly the shape of the, then we will be able to properly represent the shape of the interface. Is this point clear or not? Okay. Now, one important aspect, when we will be reconstructing the interface, we can have two types of line segments. Okay, one line segment can be something like this. Say this is my type 1 line segment. In this type 1 line segment, you can see that this particular line is nothing but intersecting with the cell boundaries, opposite cell boundaries. Okay, and if you see this particular line segment, this is type 2, where your cell, this line boundaries are intersecting with the adjacent cell boundaries. Is this one clear? So first thing is, from the slope we have come to know the direction, okay, parallel to which where we need to place the line, and then doing this area conservation, we have to satisfy the location of the line, intercept of the line, and moreover when we will be placing the line, it can have now two situations. Either this line can be intersecting the opposite boundaries of the cell, or this can intercept the adjacent boundaries of the cell. Okay, now you can see that how accurate is this scheme. So what you can do here, say these are my two adjacent cells, these are two adjacent cells. So if I say that this is my cell I comma j, then this particular cell will be I minus 1 comma j. Now in these two adjacent cells, say this is my actual interface boundary. So this curve, whatever you can see over here, this I am calling as nothing but my actual interface. Okay, and this black colored line, okay, now if what you need to do, if you need to say calculate the area within each cell using your trapezoidal rule of integration, then what we do in the trapezoidal rule of integration? So if you have arbitrary some curve and you have to apply trapezoidal rule of integration to determine the area of the curve, what we do? We divide this in small segments, okay, and this curve in each segment we approximate with the straight lines. Is this point clear? So that is what I have done over here. So if you see these dotted lines, what is this dotted line representing? This is representing the line segments of the curve if I would have used trapezoidal rule of integration to determine area under this curve. Is this point clear? Now, typically whenever you apply the trapezoidal rule of integration, then order of this is, because only we consider the linear approximation, so second order term we are actually eliminating. So truncation error associated with that rule of integration is of the order of h square, if h is my say each segment width. Okay, so then order of this scheme in the trapezoidal rule of integration will be nothing but order of h square. Okay, now here you can see, if you assume that this line is reconstructed by trapezoidal rule of integration, then how much difference of area will be there in between the actual curve and the trapezoidal rule of integration? So this is something which you can see over here in the right hand side. Okay, so this shaded area is something which is nothing but the area difference in between the actual curve profile and the profile which is obtained using the trapezoidal rule of integration. Okay, but now you consider the interface reconstruction using PLIC. So using PLIC, if you construct the interface profile, you will be finding these two lines. One is this line and then other is this line. Okay. So here you can see that because trapezoidal rule of integration, common face has to be the intercepts of the line should lie on the curve. So that's why you are having continuous transition. But as in the PLIC reconstruction, we don't have any rule that two different line segments in the different cells should intersect at the cell boundary. Okay. So here one line segment is ending at different point and other is actually starting at slightly higher location. Okay, so it means that thing is that kind of restriction we don't have. First point is that, and second point is that now if you see this line segment is actually giving this much deviation. So this is the deviation of the area in comparison to your actual curve. Okay, so here you can see that if your order of trapezoidal rule of integration for this was h square, then of course your PLIC integration will be giving slightly better approximation of the interface in comparison to the one what we have seen over here. Okay, so it means that convergence order of this scheme is actually good. Now let's talk about the methods how to calculate m. Okay, because mathematically it is very simple to write that m is nothing but equal to minus gradient of color function. This is the mathematical expression. But whenever you will be doing this with the help of computers, then computer does not understand the gradient operator. Computer will be only able to do algebraic manipulations. So that's why you have to first tell your computer that for solving this gradient, what type of mathematical, what type of equation it has to actually solve. So for that purpose, what we do over here discretization, and typically the method which I am now showing here, it is called as Young's finite difference method for estimation of the slope. Okay, so as per Young's method, what is done, say this is my cell and this particular cell is having indices I, j. Okay, now if I calculate, if I take this particular corner, can you tell me what will be the indices of this corner? Indices of this corner will be half and j plus half. Indices of this corner j minus 1 by 2. Okay, so likewise I can define the indices of all the corner points. Okay, now let me do one thing. I want to calculate, so when you will be doing this m equal to divergence of gradient of c, you will be finding it as nothing but minus del c by del x I cap minus del c by del y j cap, and this I can write equal to nothing but x component of this I plus y component of this and j. So from here you can say that the x component of the slope is equal to minus del c by del x. Okay, so what we do here first, to determine the value of the m at any cell centered location ij, before that first we calculate the value at all the corners of that cell using the Young's finite difference method, and then we take average of all these values to determine value of m at the cell center. Okay, so that is what you can see over here. Now what I need to do, I need to calculate say mx at cell I plus 1 by 2. So I plus 1 by 2 comma j plus 1 by 2. So at this cell now I need to calculate, at this corner now I want to calculate the value of mx. Mx means minus del c by del x. Okay, so from our simple understanding, it will be equal to minus of C at, if I use the central difference scheme, then what I will be writing here? Tell me. Ci plus 1. So what I will do now, there are two issues. You can see this particular corner is lying at some location which is not coming exactly at the node, which is not parallel to node locations. Okay, so what we will be doing first I will now calculate the value at this particular face centered location. Okay, so when I will be calculating at this face centered location, so this face centered location will become nothing but I plus 1 by 2 comma j. Is this point clear? So I plus 1 by 2 comma j. When I am calculating at location I plus 1 by 2 comma j value of mx, that will be becoming equal to, now you can see you have in x direction nodes aligned parallel. So here what is the next node point? I plus 1 comma j. So I can write C at I plus 1 comma I plus 1 comma j minus C at I comma j divided by h. Is this point clear? No, h. This is forward difference, sorry. Not central difference, forward difference. Because this cell is delta x, so node to node will be h. Yes, sorry, this is centered because I am calculating at the face center, no, not at the node point. So we are applying central difference scheme only, but this is the distance between the nodes is h. Yes, because we are calculating at the face center. Okay, so this is mx at I plus 1 by 2 comma j. Then what I will do, I will also calculate mx, but at what point? This point. What is this point? I plus 1 by 2 j plus 1. Is this point clear? So at this point now I will calculate. So what will be the value at this point? C at I plus 1 comma j plus 1 minus C I comma j plus 1. Is this point clear? So it means I have calculated at this face center and at this face center. Then after that what I will do, to calculate at this point, I will take average of these two. Point is clear or not? So once I take the average of this and average of the similar formulation at point j plus 1. So that will become 1 by 2 average I am doing. So 1 by 2, h is coming common from everything. So C I plus 1, j plus 1 minus C I comma j plus 1. This is coming from this face, and then C I plus 1 comma j and C I. All are clear with this point? So what is the Young's finite difference approach is that I should know first the values at all the corner points and then I do the average of all the corner values. But to know first at corner points, before that also we need to do interpolation. Okay, interpolation means first we need to calculate at the face boundaries, and once we calculated at the face centers of each control volume, then along a single edge to determine at corner the average of the face consecutive face centered values we need to do. Is this point clear? So till now I have only calculated the single component mx, and this is calculated at one corner point. Likewise, I need to apply this formula for all corner points. Is this point clear? So once I applied this for all corner points, then I will be getting the corresponding value of mx known at each and every corner point. All are clear with this idea? After this, what we need to then do? Then we need to calculate m y at each corner. So now can you tell me how this formula will be coming for my? Because for mx I have explained. What will be happening for my? How you can calculate? This is the cell I comma j. This is my I plus 1 by 2 and j plus 1 by 2. Now at this I need to calculate in which direction? Y direction. Okay. So to know at y direction, I will first calculate at this face and then I will calculate at this face in y direction. And the average of these face centered value will be my corner value at y. Okay. So at this particular face my value will become, now it is del c by del y. So value will be minus of c times at I comma j plus 1 minus c ij divided by h. And at the next point it will be c at I plus 1 comma j plus 1 minus c at I plus 1 comma j by h. And then if you take the mean, then ultimately you will be getting this formula. Now this formula of MOI again, then you have to calculate for all the corner points. Okay. And then finally, if you know individual mx and my, it means that you know the value of m at each and every corner point. Once you know the value of m at each and every corner point, then you can calculate value of m vector for ij by considering the average of all the means. Is this one clear? So this is called as Young's finite difference method for estimation of slope or estimation of normal vector to the interface in a particular cell. Is this point clear? Then comes next method. So there are multiple methods. Of course, methods are having some limitations and some issues. So then more advanced methods have been developed. So now next method is called as centered column difference method. So here also my role is to calculate the value of m only. That is my interest. But the way I will be calculating, actually that has changed. So here what I have done, near the interface I have placed a 3 by 3 stencil of uniform size. Okay, so here you can see in this direction also I have 3 cells, in this direction also I have 3 cells. So this is called as 3 by 3 stencil. Okay, so wherever you are locating the interface, say this is your cell I comma j, around cell ij you have to place a stencil of uniform size. Okay, and in this stencil the bottommost position of the stencil will become a reference value. Okay, so now say you have this particular line. So for this particular line, what I will be doing, I will be calculating the value of this value is called as, this y value is called as nothing but our height function. Okay, so I will be calculating the value of height function for the central position of, corner central position of this stencil columns. Okay, so in the left column you can see this will be value of height function yi minus 1, and in the rightmost boundary column at the cell center yi plus 1 is the value of the height function. Okay, is this one clear? Now how to calculate this value of yi minus 1 and yi plus 1? So one important point is, this value at yi minus 1 will be nothing but equal to value of this c into h, okay, plus value of this c into h. Is this one clear? So that's why, and of course in the third cell also I can do c into h and it will be actually equal to 0 only. So ultimately what I can do, this central column I can represent with index 0, the top row I can represent with index 1 and bottom row I can represent with index minus 1. So what I have done then, I have used some summation symbol over the k which is varying from minus 1 to 1, and then in this I have calculated the sum of c for I minus 1 and j plus k. So this is I am calculating with reference to position number I comma j. Is this point clear? So with reference to this position, my extreme left column has become I minus 1, and whereas the label is actually, label in y direction is, initial label will be j only, then 1 will be below this, 1 will be above this. So that's why j plus k is written and k is varied from minus 1 to plus 1. Okay. Now c into h will give me linear distance, but in order to generalize this formula, it is written as h square into c, and this is written as h into y minus 1. Why it is written h square into c? Because ultimately it will give you directly the value of volume of the reference phase. Okay, so its extension to 3 dimension will be actually easier. So that's why this h square is multiplied. All are clear with this idea? So now using this formula, if you place this stencil in any cell ij, there you can calculate the value of this extreme left height function. Similarly, you can calculate the value at j plus 1. So for j plus 1, one simple thing will be changing, that this I will be now what? I plus 1. All are clear with this point? So when I will be calculating for rightmost column of the stencil, then it will simply be I plus 1. Okay. This is one way. Now second way of representing the interface can be that instead of representing from this bottom boundary, I can calculate the value of, rather than height function, I can use my width function. Okay. So when I will be using the width function, then I am considering that my reference boundary is rightmost boundary of the stencil. Okay. So with this reference boundary, if I have to calculate the value of x j plus 1, then it will be h time x j plus 1, h square, k varies from minus 1 to 1. Now I need to move in this direction. So my x direction is changing and y is fixed. So that's why I have written I plus k and y is fixed to j plus 1 level. So that is j plus 1. Okay. So this is how I can calculate the values of height function and width function by putting a stencil on the interface. After this is known to me, then I can write equation that this is a sine function. SGN is sine function. The meaning of sine function is that if you put any integral value, then for integral value it will be simply giving the sine of that sine of that real number. Okay. So here you can see that sine of my, whatever is your my slope, it is giving its sine. So minus y equal to, if it is minus, then it will be minus y. If it is plus, then it will be plus. So y equal to minus mx dash mx into x plus alpha. So if you measure this slope with reference to the horizontal axis, then this slope will be nothing but mx. But if you measure this with reference to vertical axis here, then this component will be coming as nothing but my. So you have calculated both the ways, and then out of these, if you want to reconstruct the interface using first formulation, then you will be writing minus mx plus alpha dash. If you want to reconstruct using this formulation, then you will be writing x equal to minus my into minus my plus alpha double dash. Up to this point, is it clear? But now in this line, one important point is, how to calculate the values of this mx and my. So mx and my are calculated using the column centered approach. Column centered approach means mxc I can simply write as y value at I plus 1 minus y value at I minus 1 divided by distance between these 2 points, which is from this point to this point, and this distance is 2h. Is this point clear? So if I know the value, it means that if I know the value of height function, then with the information of this height function I can calculate the value of mx slope. Okay, slope with reference to x direction. But you have to remember one point, that this slope is calculated using the cell centered approach. The meaning of cell centered approach is, in this column I have actually calculated y value at the center of the column. Okay, is this one clear? So that's why it is called as cell centered approach. Now if you do substitutions of yi plus 1 and yi minus 1, then ultimately this equation can simply be written in terms of purely color function. Okay, so once you know color function, it means you need not to do calculate these heights. You can simply calculate the values of the slope. Similarly, if you have to calculate slope with reference to y, then it will be becoming x at point j plus 1 minus x at j minus 1 divided by 2h. And using any of these lines, you can actually reconstruct the interface profile. Okay, but this cell-centered approach is having one limitation. What is the limitation? If your, earlier I told you one important point, I highlighted it 2 times. What is the reason? Now you will be understanding. I told you when using the PLIC, we will be reconstructing the interface profile. Either that PLIC line segment can cross interface at opposite cell boundaries, or it can cross at adjacent cell boundaries. So if your line segment is crossing the opposite cell boundaries, then there is no problem. Whether you calculate value of height function at cell center, or if you calculate at right corner of the cell, or if you calculate at left corner of the cell, every time it will be giving the same value of the slope. Is this one clear? Every time, because all are lying on a single line at opposite corner, so every time you will get a same value of the slope. But if you have your interface line something like this, where it is nothing but crossing the adjacent cell boundaries, not the opposite cell boundaries. In that case, what will be happening? Now if you approximate using this equation, you will find some value of y which is higher than the actual interface C. Is this one clear? All are clear with this idea or not? What I have done, say here, this is crossing like this. So now, when I am calculating this value of yi minus 1, this is based on the amount of volume covered in this zone. If amount of volume covered in this zone is more, then value of height function will be keep on increasing. Okay, but and ultimately whenever you will be using this calculation of slope, you will be using this particular value for estimating the slope. So ultimately your slope may come, say something, your line may be reconstructed like this, but your actual value of the interface is actually very less. Okay, so when your line segment, PLIC line segment, is crossing the adjacent values of the adjacent faces of the cell, in that case actually this column centered difference method gives errors. Okay, is this point clear? So it means this is not a foolproof method at the moment. Then what is done if your slope is if situation is like this, that mx is equal to 1 by my is less than 1. Second situation can be my is 1 by mx which is less than 1. So typically what is done, if you are calculating using the cell-centered approach, then m star is considered as minimum of xc and yc, and using this m star you reconstruct the interface profile. Because for constructing the interface, either you need mx or you need my. Okay, only one will be sufficient to plot your interface value, reconstruct your interface profile line segment. So the way out is that out of these two values which are calculated based on the cell-centered approach, just go for the minimum value and using that particular formulation choose the equation and then construct the interface profile. All are clear with this idea? Then comes I will explain in the next slide. Now, next method is efficient least squares volume of fluid interface reconstruction algorithm, Elvira method. Okay. So what Elvira method does, in the column centered approach, what we did, we have chosen the minimum value of the slope. Okay. Elvira method actually provides us with large number of options of the slope. Okay, so how large number of options of the slope? It tells us that I will not only restrict myself to the center of the column, but I will also calculate the value of height function for right corner or for left corner. Okay, so when I am going from the cell centered position to right corner, then it is called as forward slope. The slope which is calculated using the right corner, that is called as forward slope, and the slope which is calculated using the left corner, that is called as backward slope. So now I have option. So it means that in single x direction, how many slopes now you have? One is cell-centered, second is forward, and third is backward. So it means 3 options for x slope and 3 options for y slope. And in total, how many slopes are needed? Only 1 is needed to construct the interface. Now you have to choose out of 6 only 1. Okay. So for that, now the way algorithm is written for centered approach, similar way it can be written for backward and forward approach. I think I need not to explain this again. Okay, so you can easily derive it from the previous discussion, the way I have done it for cell-centered approach. Okay. Now, what we do here, we calculate actually error function in terms of least squares. Okay. So, let us assume that using any slope, first I have defined the line, and corresponding to that line segment, I have actually got some value of volume fraction. And whatever value of volume fraction I have got, let me call that as nothing but C tilde. Is this one clear? So C tilde is the value of volume fraction which I have got when I have used out of 6 any one of the slope value. Okay. Now if I have to define error function in terms of least squares, which is typically called as variance, so what I will do, what was my actual value of color function? That was nothing but C. By using this value, I am trying to reconstruct the interface profile. Okay. So this is my actual value of the color function, and this is C tilde is the value of color function which is obtained after we have chosen any one of the slope. Okay. So difference of these two and then their square is multiplied with h square, and if I take this summation for the complete stencil, that becomes nothing but my entire error function. And you have to remember one point over here, when I am doing this summation over the entire stencil, first for entire stencil it will be using a single value of slope, then it will be using second value of slope. So it will be using all the values of slope in this single error function. And we will be determining the value of error function for whatever slope is actually least, we will be actually choosing that particular line segment out of 6. Okay. So this method gives good amount of accuracy, but the issue with this method is whenever you extend it for 3 dimensions, then the number of slopes becomes too many and this number of computations becomes large. So because of which actually ultimately what happens, the speed of the algorithm becomes slow or computational cost is actually extremely high. Okay. Then the next method, this is least squares fit method. So in case of least squares fit method, what is done? If you have actual interface profile, say this actual interface profile is first reconstructed using any of the preliminary method. Preliminary method means, say if you use Young's finite difference method, whatever I have specified earlier. So with that method, whatever initial interface profile you are getting, just plot it. Okay, and then divide this line segment into 3 parts. In a computational cell, divide this into 3 parts. Is this point clear? And then you take the help of these 3 points to construct your actual interface profile and define some error function and try to minimize the value of this error function. So my error function is I varies from 1 to np, where np represents the number of points which I have divided, and wi is simply a weight function. What is yi? Yi is actual value of interface at all these 3 line segments, and mxi plus alpha is the these values of this vertical height which are calculated using this fitted line. Okay. So what will be your ultimate aim? Your ultimate aim will be to orient this line in such a way to move this line up and down, or orient in such a way so that you are getting equivalent area also and you have least distance from these points. So what you need to do, you need to minimize this function, any of this function, either this or this. So if you use the height function, then you will be using first one. If you use the width function, then you will be using second function. Okay, so you have to minimize this and compute the values of m and alpha for which actually you are getting the least amount of error. Okay, so this is nothing but if you simply do your if you go to your Excel, and in Excel what we do curve fitting. Okay, so all of you might have got some experimental data, and after you have got some experimental data, say your experiment is showing the linear dependence between the 2 parameters which you have measured, then if you plot, then the scatter points, if you fit in Excel, you just simply do a single click that you have done linear fit, but at the background it solves this set of equations to give you the best possible linear fit among these data points. Okay, so here what we are doing, we are artificially creating 3 points in the cell and then we are using that information to minimize the cell. So now this rightward figure, you can see that how in each cell, so this is the first cell, here you have used 3 segment points. This is second cell where you have used 3 segment points. This is fourth cell where you have used 3 segment points, equally spaced points. If you use all this information and then using this information you reconstruct the interface profile. So this dashed line is the minimized reconstructed interface profile which you have got out of this. Okay. So typically this is the solver like in different solvers they use different types of approaches. So for example, in one of the solver free source open source software Jeris, so Jeris uses mixed centered column and Young's finite difference approach. So they have done hybridization of both to calculate the interface profile, and then they specify this. So some solvers uses this particular method, so least squares method, to determine the interface profile. Okay. Then in an entire discussion I have explained you about the placement of the line with reference to the conservation of area. But that area conservation operation is also something which your computer will not be understanding self. You have to instruct computer that okay, do this calculation, then only it can calculate the value of intercept alpha in order to determine the exact location of the line, whether to place line at this location, like in this direction or in above direction. Okay, because by knowing M only we know the orientation, but after that orientation at what location we need to place this line, that is something which is determined by alpha. So for doing alpha, again we have to do some minimization function, and this minimization function g of alpha is equal to A alpha. So it means area of the reference phase when you have selected any arbitrary value of alpha, and minus delta x delta y into C. So delta x delta y is cell size, multiplied by C will give you the area occupied by the reference phase. So this value is something which you have to minimize. Okay, so for two-dimensional situation, mostly you will be finding, if you have a structured grid, that this is your XY system and this is the cell in which you want to represent this line segment. Okay, so you can use, first you can see that this, if you place this line segment like this, then this shaded portion becomes nothing but a polygon. Okay, and different sides of the polygon are A to B, B to F, F to G, G to D, and then D to A. Okay, so if you have to determine the area of this polygon, then you can utilize this rule, diagonal rule, that half of summation k varies from 1 to n, because if you have to minimize this function, for minimizing this function first you have to know this A of alpha. So A of alpha, say you have placed line like this, now you want to determine this area. So using this system you can measure it, k xky k plus 1, then minus xk plus 1 into yk. So this is a direct formula for estimation of area in a multi-sided polygon. Okay, here one thing you will be finding, when your value of k will become equal to n, then this index will become n plus 1. So what is the value of index n plus 1? So this is nothing but n-sided polygon. So if you start from this side, this is your n equal to k equal to 1, n plus 1 will be again marking the same point, because you are closing now the polygon. Okay, so this is one method for estimation of area. Other method for estimation of area can be this. So what you can do, first you can calculate the area of this big triangle A, E and H. So area of big triangle AEH is alpha square divided by 2 mx and my. What is area of the triangle? Half into, so here base will be becoming alpha by mx and height will be becoming alpha by my. So that's why this is the area of this big triangle. Then minus some function which is a function of alpha minus mx into delta x. This is giving you the area of triangle segment BEF. Minus f2 into this function, this is giving the area of triangle segment DG and H. So ultimately then you will be getting this shaded portion. Okay, so of course here you have to remember that f2 function is nothing but a square function. So f2 of any quantity is square of that particular quantity when z is greater than when this entire value is greater than 0, and f2 of z will be equal to 0 if this value is less than 0. Okay, so this is a generic, these are some generic formulas which you can utilize to calculate area once you have placed this line at any arbitrary location, and once you calculated this area, then you have to minimize this function g of alpha to determine the exact value of alpha for which actually this condition is settled. All are clear with this point? Of course, you cannot make this completely 0 because of the numerical computation. So, the way you specify residual for your continuity and momentum equations, in the similar way you have to specify some convergence criteria for this function also. Okay, and then you can reconstruct the interface profile. So, you can see now that the process of reconstructing the interface is not very simple. So, how many computations, and this I am explaining all these computations in a single cell. If you have say 1 lakh cells, 5 lakh cells present in one system, then for each and every cell you have to do this computation. And you have to remember also one more point, whatever discussion we have done till now, that is for a structured Cartesian grid. If you go for unstructured mesh, then your computation will be even more challenging. Okay. Now you can see the extension of the same for a 3-dimensional control volume. Of course, I am not going to explain this, but this is a hexahedral control volume, and if you have to place anything, that will be becoming nothing but a plane segment. Whatever is lying in 2 dimension, in 3 dimension, that will become a plane segment. This is the representation of a plane segment, and this is the equation of the plane. And here you can see in this control volume, this is the cell centered location, this is the corner index I plus 1 j plus I plus 1 by 2 j plus 1 by 2 k plus 1 by 2, and then these blue colored things are nothing but neighboring cell centers. So again, you know the values, how you can calculate the values of m and this. So here there is slight change of symbol. So delta is replacement of h and alpha is replacement of color function c. Okay. So these are the equations which are given, that in 3-dimensional system, if you have to calculate value of m slope, then how you can calculate and then finally construct the equation of the plane. Okay. And of course, for volume estimation also there is formula like area estimation that I have not included over here. Okay. So with this we have come to know little bit about the reconstruction of the interface. Okay.